You're being recorded from now on. All right. Okay. Okay, so you can see the screen here. All right, very good. The owl is not working. Canvas is not working. What's going on today? All right. What is going on? I actually can turn off the background too, right? And I can actually see the background of what I'm showing you. Where do I do this again? Okay. Video. Background and filters. Let's take the background off so you can at least see what I'm pointing at. Since the owl is not working, that's the best we got. Sorry about that.
Something's better than nothing.
That is true. That is true. I like the spirit. Thank you. Good. All right, what we got? We have syllabus here. You all got started now on the graded lab number 1. Please do submit that. I think the deadline was last night at midnight. If you send it by tonight midnight, you won't get points reducted. I hope nobody really had serious issues with that. Ari indicated it was learning curve. I hope it was, because that's the purpose of it. It's the first time that you autonomously start to grade and to code something. And this is really the idea. And this is continuing today. This graded lab number 2. Hi, how are you? Come on in. And this will essentially be the next step of where you autonomously code. The idea is to really prepare you already for the final project. Careful with the output. But it's not working anyway, so might as well put it away. So the final project, you're going to be coding independently. And for that, it's crucial that you kind of have a good idea and a good grasp on how to code things in principle. Graded lab is going to be a little bit harder than graded lab 1. And next week, we're going to do graded lab number 3. And then you're on for a smooth ride. And then it's just graded practice labs that basically I will be coding for you. Good. So we're also going to do, in 2 weeks, we're going to do quiz 2, which is going to be covering all topics that we had up until then. This time it will involve some coding and some calculations, but they're super simple. They're nothing scary. And yeah, so it's basically, it's the same face value as the first quiz. It's going to be 50 points out of those 1,000. And then I also want to really emphasize that the first draft of the analysis plan and the final report is due on 11/18. So that's like in less than 3 weeks, somewhat in 3 weeks. Please make sure that you have investigated a little bit the enhanced data set and that you have thought about potential research questions. I think I provided resources to that extent that you can look up potential research questions. And if you send me stuff beforehand and you email me ideas, we can work together beforehand already to refine those a little bit, that you beat the time. Because I want to avoid this, that you then a couple of days before the 18th, you're basically starting off with developing your research ideas and formulating your hypothesis. So I think it's better to kind of start early in the game. Good. So any questions about the syllabus, about things that essentially will come your way in the next weeks? If not, then we can essentially start talking about what we're going to talk about today. So we continue today to talk about point estimates, confidence intervals, and hypothesis testing. And today it's going to be a little bit more practical. So today we're really going to start into how to calculate confidence intervals, how to calculate p-values, with the idea that you kind of really understand the background of p-values. So p-values are often quoted. Hypothesis testing, you see this basically in every scientific article, you see p-values all over the place, and it's often used for correlational or comparative analysis. You compare two groups, you compare two samples, you're doing hypothesis testing at this point. So every comparison, every p-value basically has an underlying hypothesis and underlying research questions, meaning that you have one comparison with each p-value. And it's important to understand that it's not only about the p-value, it's also about the variability of the distribution. And you really also need to understand and feel the data, how it really looks like. So it's not only about this p-value. You really need to also understand that the differences that you actually see in comparative analysis do actually matter more than the p-value at times, because you have a large enough sample size, you essentially will always by default get a significant p-value. So it's really the difference that is actually more important, that you need to put more weight onto when you interpret the results. Good. So we will be talking about hypothesis testing today. We will be talking about hypothesis testing and test procedures, which will essentially involve really the calculation of p-values. We will talk further about the t-distribution and confidence interval estimation in the light of the t-distribution, and two-sample hypothesis testing, which essentially gets us now to the next level, away from set scores and set statistics, where we basically compare sample statistics to population parameters. So let's get started with the lecture per se. I understand that this class, to some extent, involves a lot of lecture, a lot of theory, but it's basically more meant as a kind of hands-on exercise. A lot of it will be hands-on, but to do hands-on and interpret results, you need to understand the underlying dynamics and the underlying arithmetics, at least to some extent in the broader stroke. And that's why I'm going through lengths to discuss this with you. And I think it makes a lot of sense to at least understand the basics of it. You probably will never in your entire life calculate a p-value again, but I think it makes sense to know in principle what it entails, what it means, and how you actually should interpret it in the greater scheme. So today we will be talking about relationship between confidence intervals and hypothesis testing, because confidence intervals, when you put them at the same alpha level as hypothesis testing, essentially can replace hypothesis testing, or at least supplement the hypothesis test per se. We will be talking about hypothesis testing of population means and population proportions. We will write null and alternative hypotheses. We will calculate test statistics and p-values. We will perform one-sided and two-sided set tests and t-tests for one sample, and define type 1, type 2, and power. Type 1 and type 2 error and power. So taking a step back and talking about confidence interval. So we spoke last time that confidence intervals provide estimates of populations. So basically you will have a sample, and based on this sample, you will calculate a mean. The larger the sample is, the more likely the mean of the sample will be identical to the population mean. When you look at samples, essentially, you will then not look at the raw scores in the sample. You will consider the samples essentially as one sample that was drawn repeatedly from a population, and essentially the sample mean will reflect this mean of several samples that you have drawn in a more virtual sense, so to say. And the underlying variability that you will be quantifying is the standard error of the mean, which essentially is the variability that you would expect from these means, from these repeated samples that you have drawn. And these will be related to the standard deviation of the population by a division of the square root of the n. So we have discussed the central limit theorem, which essentially underlies this association. So when talking about the confidence intervals, you take this distribution of the sample mean, and you define, based on the alpha level that you have defined, a probability that essentially is determined by an interval of 2 points on the normal distribution curve of the distribution of the sample mean that will include your actual population mean. So essentially you have a level of confidence which reflects that probability that that interval that you have defined contains the real population mean. So now you can already think about what that means in terms of hypothesis testing, because if you compare the sample mean to the population mean and you're quantifying a p-value, which is a probability that the sample mean indeed is significantly different from the population mean and not drawn due to random variation of chance from the population distribution, essentially by that you essentially build the bridge between confidence interval, the interval that contains the population mean, and the probability that this sample mean and this distribution of the sample means and the mean of means of all these random independent samples does indeed significantly differ from that population mean. So this is the connection. The p-value and the confidence interval essentially have the same alpha level as the underlying assumption. So the estimated and confidence interval provides a range of population means that are consistent with the sample. So this margin of error essentially is calculated just like depicted here. We have a confidence interval, we have a sample mean x bar, which is dependent on the n's, plus minus a t or a set that basically is multiplied with half of the alpha with the degrees of freedom from the t-score table. That essentially implies that now when we're talking about the t-distribution, we're looking at the t-distribution and not at the set distribution anymore. And the t-distribution does resemble a normal distribution. And this is why we're essentially looking at it from the angle of degrees of freedom and not from the actual sample size anymore. And the so-called set score, which essentially is defining the distance from the mean as distance measured in standard deviations. So essentially we have a t-value that essentially resembles now the alpha level. And we're multiplying it by standard deviation divided by the square root of the n, which is the standard error. So what this means is that when we want to look at an alpha level of 5%, we essentially need with a degree of freedom of 22. So this is the t-score table, which we have discussed last time in the context of the t-distribution. We're going for a degree of freedom. And with the degree of freedom, we essentially can follow all the way to the column where we have two tails of 5. And we will find here the 2.07. So what you essentially need to do now for a degree of freedom of 22, you would need to take the sample mean and you calculate plus minus 2.07 multiplied by the standard error of the mean. That gives you the upper bound of the confidence interval. If you subtract from the sample mean, you get the lower bound. Keep this in mind because I'm flagging it right away. This will be on the quiz in 2 weeks. So this calculation really review in detail. So this is how you would calculate this. If you look for a t that is consistent with 50%, you would need to go for 0.69 of a t-score, which is an example that will not really happen in real life. So the key points are that the relationship between sample distributions and confidence intervals are here really that you will quantify this on the sampling distributions, on the distribution of the sample means, and you will use this to quantify the confidence intervals. These confidence intervals contain the true population mean, or are being used to compare two samples from each other. And you can estimate the CIs from data from your actual sample data. So why is hypothesis testing important? And this is a review from last class as well. Because hypothesis testing allows a yes and no statement. So you want to know whether a sample mean differs significantly from a population mean. You want to know whether a sample mean from one sample differs significantly from another sample. So for this reason, essentially, you need a yes or no answer. So you will always use a null hypothesis and an alternative hypothesis, a research hypothesis, where the null hypothesis implies that there's no difference between those two means, whereas the alternative hypothesis actually implies that you will accept that there's a significant difference between those two means. You can use this in various contexts. One of the contexts that's mentioned here is that the population mean has a hypothesized value, and you want to see whether your sample is significantly different from this population, or whether an intervention caused a measurable effect that you actually can quantify. And you can quantify whether this was indeed a significant difference, a significant intervention. Questions of that kind are essentially those that are mentioned below. So basically, do, for example, have hypersensitive smoking men have the same mean cholesterol level as the general population? Or questions like, does intermittent screening and treatment for malaria improve health and education of school children in certain areas? These are questions that you could ask, for example, right? And there's actually an example of a cluster randomized trial where essentially you see that these confidence intervals and these p-values essentially are helping to estimate risk ratios, which essentially indicates that the intervention that you have employed to your study population actually has caused a significant effect on the risk of a certain intervention. So this emphasizes how important p-values are and how important it is to actually know how to do hypothesis testing. So there are a couple of logics that are being implied. So observations come either from one or two population distributions. So either you have a population that you essentially test before and after, which is what we will do with the paired t-test, or it is comparing a difference between both groups. Or it can be a potentially new distribution induced by an intervention or a changing conditions. So this would be before and after situation as well. Classically, one sample hypothetical inference is that a few beans of this handful are white. You look at a bag from which you have drawn this handful of beans, and you essentially see that most beans in this bag are white. So if these beans that you have in your hand are only white to a small proportion, the beans are likely being drawn from a different bag. So the way how this would essentially be employed is by looking at it in a way that you have either a true difference, and this true difference is where the research hypothesis is indeed true. So you have truly guilty if you use this courtroom trial analogy. So you have a true alternative hypothesis, and you can either accept or reject the null hypothesis. If you accept something that actually, if you accept the null hypothesis that actually should have been rejected, you miss a significant difference. This would imply that you have a false negative that essentially is a type 2 error. This being said, this is one of the biggest problems that you actually will have in all trials that you will design, because type 2 error would be something that happens if you have a sample size that is too small. As an example, as we will discuss with power, with statistical power. if you're rejecting a null hypothesis that should not have been rejected, you commit a type 1 error. And the type 1 error you have to look at that you're taking a wrong decision and you're creating a false positive. And the false positive is actually as problematic as a type 2 error, because you're seeing a difference that you should not have seen. Happens, for example, if you subset your data and you use samples that you shouldn't have compared in the first place. That's, for example, one of the causes of type 1 error that's often seen. And then you see right decisions when indeed the null hypothesis is true and you're accepting the null hypothesis, you're taking the right decision. So this would be a true negative. If you reject a null hypothesis that is indeed not correct and you're accepting the alternative hypothesis, you're taking a right decision and you have a true positive. So type 2 error is a false negative, type 1 error is a false positive. And this is as an example how you can think of it. And this is how you can memorize it. So type 1 error, you're actually diagnosing something as being significantly different that should not have been diagnosed as being significantly different. Whereas the type 2 error is something where you have something missed. You didn't diagnose something that should have been diagnosed as significantly different. So this nicely illustrates how to look at this. So how does the confidence interval now relate to that? So essentially, you know that the mean is a set score of 0, right? So this is essentially where the sample basically is set at 0. And then you're defining your set scores or your t-scores analogously. Your set scores indicate the distance from the mean in terms of the standard deviations. So with the easiest example of a set statistics, you just need to go as far as to the point where you only have to the left here 2.5% of your probability. Whereas to the right, on the right tail, you essentially also have 2.5, and that in total gives you the 5%. So the definition of your hypothesis test is essentially that you are looking at a difference of the distribution of the sample mean, and the population mean is as extreme as one of these values. So it exceeds the bounds of the confidence interval. So when you see a population mean outside of the confidence interval, you're essentially looking at a significant difference. And the alpha level here is essentially what we have labeled before as the type 1 error. And this is your alpha level. Whereas this wrong decision is essentially 1 minus the beta, which we will discuss today. That is 1 minus the power. Good. So the set score is calculated using the standard error. So it's not the standard deviation. That would be the set statistics per se. It's the standard error that essentially is used for set statistics and hypothesis testing, because you mean to quantify the distance of the mean in terms of the variation of the sample means, the distribution of the sample means. You have essentially 5 steps of hypothesis testing you have to undergo. I also flagged this for the quiz. So you have to state null hypothesis. This you will also need to do for the analysis plan. You have a null hypothesis, which is basically characterizing your research question. And the null hypothesis will indicate that there's no significant difference between your sample mean and the population mean, or the sample mean and the second sample mean. So if you compare male versus female, your null hypothesis is that there's no difference between the mean of males and females. You need, as a second step, you need to specify the significance level, which is in 90%, 95% of cases of all scientific studies, essentially 5%. You will need to draw a sample of the size n to compute the set statistics. You use a normal distribution set when you know the true population standard deviation sigma. Or you use a t-distribution when you have to estimate your standard deviation from your sample. Then you will use a t-distribution. This is under the assumption that you have a normal distribution or you have a sample greater than 30. Based on this, you will determine the p-value. And the p-value will allow you, right, let's move this a little to the side. This is better, right? Okay. So the p-value essentially allows you to reject when it's smaller than 5%, and it's really the probability that this sample and the sampling distribution does significantly differ from your population distribution. So that means this is essentially indicating that that sample was essentially drawn from something that from a population distribution, a sample distribution that is significantly different, and it's not due to random error drawn from the same population distribution. So this p-value essentially allows you then to compare your p-value and your sample to the significance level alpha, to the type 1 error, and if it's smaller than this alpha, you essentially are rejecting the null hypothesis. If it's greater than the alpha, you will accept the null hypothesis. And you state the conclusions in this context and based on these insights. So first step is essentially formulating the null and alternative hypothesis, states that there's no difference from the past or for what you would expect. Posits the distribution for the population from which the sample was drawn reflects no change from the past. And if true, discrepancies are only due to chance. That means that the p-value is greater than 5%. Then this sample was drawn from the population distribution. Alternative hypothesis is essentially indicating the inverse, so the opposite. So if the p-value is smaller than 5%, we're accepting the null hypothesis and we're saying there's a significant difference between sample mean and population mean. You would state this in a notation that you say your mu or your x bar is equal to the population mean or it's unequal. So for the example that we will be looking at, is the blood pressure of smoking males the same as in blood, no, it's actually blood cholesterol, it's serum cholesterol. Of smoking male is the same as the general population with 211 milligrams per deciliter. But this is the example we will be working through now. So we're assuming the serum cholesterol level of the US population in average to be 211 milligrams per deciliter. That's data from a large scale study in the US. And you essentially accept this as being the same when you look at the null hypothesis, and you reject the null hypothesis if it's unequal. You can do two-sided hypothesis tests. I'm also flagging this for the quiz, the difference between one-sided and two-sided. So essentially you have two-sided tests is mu1 versus mu2. So essentially there you're comparing two samples. And this would be the same as in this randomized controlled trial about malaria interventions, where we have the proportion of control group of the control sample equals the intervention group, PT. One-sided analysis essentially are measuring directional differences. That would state that the null hypothesis, the mu of the sample or the mu of your sample is smaller or equal than the population mean. For two samples, this would be mu1 smaller than mu2. So the alternative hypothesis is essentially directing the probability of the direction being in the opposite direction, which is arithmetically different. The choice of a one versus two-sided alternative depends on the context of a problem. And it seems logical, but it's not always logical. It's not always, well, it's logical, but it's not as easy as it is with a two-sided test. A two-sided test basically just means that the population mean is outside of the bounds of the confidence interval. So it's basically larger than these critical thresholds given by the alpha value. Yeah. Secondly, you're basically specifying a significance level alpha. So you are setting the alpha to a level that you accept and that you deem acceptable, which in most cases is 5%, can also be 1%. And the alpha is also the type 1 error rate, where you basically reject the null hypothesis when the null hypothesis is true. The calculation is done as stated here. So you're subtracting x bar minus the mu of your population, and you divide it by the standard error. Here calculated the standard deviation divided by square root of the n. This gives you the set statistics for your test. For the t statistics, so the difference between set statistics and t statistic is that you're comparing your sample from a population mean, but for the set statistics, you have the true standard deviation given from the population. For a t statistics, you're estimating. So whenever you're estimating it from the sample, your standard error of the mean, you're prompted to use a t distribution. So don't forget that. That's also important. So essentially, this is the graphical depiction of what I've just said. So you have a null hypothesis value, which is your mean of the sample. So this is the sampling distribution of the test statistics, whether it's set or t. It's a normal distribution curve, and you have a sample value of a test statistic that exactly indicates that calculated set score, which is calculated using this formula. And everything greater than that essentially are values that are greater. So meaning that the population mean would be here beyond this threshold. If you calculate a p-value, the p-value is essentially a probability value. It is the probability in the tails of the sampling distribution beyond the value of the test statistics observed for this sample. So essentially that means it's the probability that the true population mean is actually beyond this threshold, and that your sample essentially is significantly different from the population mean. If it's greater than 5%, essentially it's drawn from the same population and it does not differ from the population distribution. So this overlap between your calculated set statistics and the population distribution essentially determines your p-value. And we will do this now in an example. So you accept it if the p-value is smaller than your alpha. And you accept it when it's larger than the alpha, you reject it when it's smaller than the alpha. So again, these are the 5 steps. And now we're gonna, these are the 5 steps. So hypothesis, significance level, drawing the sample, calculating the set statistics, determining the p-value based on the set statistics, and then interpreting the p-value in the light of your thresholds and your alpha. For the purpose of proportion and for the purpose of interventional trials like here, it's a little bit different because essentially you have different outcome variables, right? So you have proportions. So when you look at this example here, when you look at this, what would you say is here the outcome? It's a little trickier because here essentially your outcome is actually a proportion. It's a risk. So a risk essentially is nothing else but a proportion where you basically have a certain proportion of the population developing some condition. In this case, it's the positivity of RDT. This is the risk of being positive for Plasmodium falciparum, which is one of the kind of malaria antigens. And to see this risk, essentially this is your outcome. This is the outcome you're basically comparing from a value of 1, where the 1 essentially indicates that there's no difference between the intervention group and the control group, because the risk difference and the risk ratio between both groups is the same. So it doesn't differ in terms of risk ratio. So the 95% confidence interval essentially is to be seen in comparison to a 1, which indicates no difference. So your outcome here is essentially that risk that risk ratio. So the way you would interpret it, so there is a marginal difference, which is non-significant, of 3%. So essentially it's 1.03 indicates that there's a difference of 3% between the groups, which is not significant and as such to be deemed a non-significant treatment effect. The significance level is given as 5%, and the p-value here essentially is given as p equals 62%. So there's no effect, and it's not rejected because it's greater than 5%, right? So this is how you have to interpret then interventional trials that basically quantify risk in populations, in study populations. So now let's go back to our continuous variable example of the two-sided Z-test for cholesterol. So we are considering cholesterol levels normally distributed with 211 milligrams per deciliter. That's our population mean, and we have a sigma of 46 milligrams per deciliter. This is given from a large-scale study in US men. And now essentially we want to state a null hypothesis where we're comparing a sample mean, mu, to this mu zero. Alternative hypothesis would imply that this mu of your sample is unequal to 211 milligrams per deciliter with an alpha 5%. We're testing two samples. One is 195, the other one is 227. The sample contains 25 hypertensive male smokers, and this is the population we're looking at. You basically, what you're doing is you compare this difference by subtracting 211, which is our mu zero, from 195, which is the mean of our sample population. We're dividing it now by 46, which is our standard deviation, right? That's the true standard deviation, so it's a set statistic. And this 46 is divided by the square root of 25, gives us a set score of minus 1.74. I flagged this calculation also for the quiz. So essentially what you're doing, you're getting now a set statistics. And this essentially implies that this P is for one side 0.041. And this comes from the set score table. You look up on the set score table. No, there's none. From the set score table, you're looking up minus 1.74. And you find the corresponding probability as 0.041. You have to multiply this by 2 because it's a two-sided Z-test. It basically entails that both sides need to be taken into account. So it indicates as a research question, is this value as extreme as 5%? As extreme as these values essentially present on the normal distribution, on the sampling distribution. So that's why you have to multiply it by 2. For the one-sided test, it's a little trickier because you don't multiply it by 2, but we get to that. So the p-value would be the same if you take an x bar of 227, because 195 minus 211 is minus 16. 227 minus 211 is also 16, but it's plus 16. But since you're getting either minus 1.74 or minus 1.74, and you're multiplying that corresponding p-value with 2, you essentially get to the same value. So you're not rejecting the null hypothesis, and you essentially accepting the null hypothesis, not rejecting it. So we are not 95% confident that the null hypothesis is true. We're just saying that we are 95% confident that the null hypothesis shall not be rejected. When we're doing a one-sided test, it's a little trickier because essentially you are looking only at that p-value that is given with the alternative hypothesis. So if you have a mu of the sample that is smaller than 211 as your alternative hypothesis, and the null hypothesis, the mu of the sample is greater or equal than 211, you're only taking everything to the left because your alternative hypothesis indicates that it's smaller than the 211. So you have minus 1.74 corresponding with a p-value of 0.041 essentially is a significant difference because it's smaller than 5%. So now the null hypothesis is rejected. If you are having an alternative hypothesis that you're interested in whether the sample mean is greater than 211, then you would essentially look to the right side of your distribution. And you would quantify the probability to the right side of your distribution. And that would essentially be 1 minus the 0.041, which is here 0.96. That's when you do not reject the null hypothesis, because it's not significantly different. So the take-home message is essentially that the one-sided p-value is half the two-sided p-value. That makes it smaller and makes it more likely to be rejected when it points in the direction of your null, of your alternative hypothesis. One-sided tests are a rarity, are not used very often, and basically all journals will prompt you and will ask you to submit two-sided hypothesis tests. If you're testing for proportions, you essentially have an x equals 0, which is no event, and a 1 for an event that occurred. You basically use this as in the same way for continuous data, but you're calculating the set as the difference between the proportion of the sample minus the proportion of your population, and you divide it by the standard error of the mean. And the standard error of the mean is calculated how we have calculated the binomial distribution as the sample probability or prevalence, often condition, multiplied by 1 minus that prevalence, divided by the sample size. And then this resulting value, you employ the square root on. Gets you the standard error, allows you to quantify the set with what we discussed as the normal approximation of the binomial distribution. So merging the tests essentially allows you now to do hypothesis testing using the confidence intervals. Because if you have confidence intervals, you can use these to test your sample mean. If your population mean or sample mean that you're comparing it to falls within the confidence interval of the corresponding other sample, or your population mean falls within that confidence interval of your sample, you fail to reject your null hypothesis. If you have an X bar that essentially does not contain your population mean, you're rejecting the null hypothesis. So we have 211, right? 211 is contained between 182 and 218. 211 is not contained between 172 and 208. 211 is not contained in 221 to 257. So this is when you reject. So that's when you can reject it as a binary outcome. So either you reject it, yes, no. It's not a quantitative way to quantify the p-value, as you will need it for some of your analysis. For the final project, for example, you're being asked to do hypothesis testing by computing actual p-value and draw your conclusions based on that p-value. You got to be careful that overlapping confidence intervals, when just the confidence intervals overlap, that does not mean that two samples are significantly different. If the focus should really be on the mean in the light of the confidence interval of the other sample. So if that mean of the second sample is outside of the confidence interval of the first sample, then you can draw a conclusion about a significant difference, but not just over the overlapping. But we'll talk about this more when we talk about two-sample testing. So now when you speak about type 1 and type 2 errors, where you rejected something that you shouldn't have rejected, and you have committed a type 1 error, or you have not rejected what you should have rejected and you committed a type 2 error, you essentially also need to understand how to interpret this. So when you have an alpha, that's your false positive rate. That's the false positive rate you're willing to accept. If you are indeed making the right decision, so you're rejecting or you're not rejecting what actually shouldn't have been rejected, that's your true negative. That's a probability of 1 minus alpha. If you are committing a type 2 error, that is the probability called beta. This is a false negative. And not committing an error is a probability called power. And this is calculated as 1 minus the beta. So this is when you reject the null hypothesis that actually was false. And we will continue to talk about power in the next class. What is important to understand is that the type 2 error decreases and the power increases as the alternative hypothesis gets essentially further away from the mu0. Mu1 is further away from mu0. So when you, for example, you test an intervention of whatever randomized controlled trial you're conducting or planning or designing or writing a protocol for, the larger the difference between your initial sample or your mu0 or your control group and the alternative sample, the larger the difference, the more likely your power is going to be large. The type 2 error will decrease when your variability decreases, obviously, because the variability will determine the standard error of the mean. And the variability and the standard error of the mean is also dependent on the sample size. So the larger your sample, the more likely you will also see smaller variability. With smaller variability, you will more likely see a significant difference between your two samples. The type 1 error remains the same. So it would always be the same alpha. That doesn't change. So you essentially want the power as high as possible, logically, because you don't want to miss a difference. Because you got to think of it from the angle that you're submitting your grant, you're submitting your study protocol somewhere for funding. You say, okay, I want to test my invention. I want to test my intervention that I've developed. I believe in that. And I expect that difference and I expect this variability. And I need to study XYZ patients. I need to study 200 patients. So they will give you money based on how many patients you plan to study if your hypothesis is really good. The problem is that you will need to determine for them what your power will be. So that power needs to be large enough that you really pick up differences that you should have picked up. So that power should be at least like an 80 or in most cases the demand of 90%. Because the problem is if your power is too small and the sample size is too small, you're missing a difference that you should have caught. And then essentially the NIH gave you $1 million and you don't see this difference because you didn't study enough patients. So that's an obvious problem, right? Because somebody is not going to be happy to have spent all that money on your study. So this is why power is really super important. And this power really protects the investigator to have a negative study and false negative study that actually should have reacted or should have actually shown a significant difference. On the other hand, the alpha protects the public and the scientific community from having something presented that should not have been presented as a significant result. So you really need both in the interplay to basically draw solid conclusions and robust insights. So if you fail to reject the null hypothesis, the probability that the null hypothesis is true is not equal to 1 minus alpha. It just means that we failed to reject the null hypothesis, but we cannot say that the null hypothesis is indeed true, because it could still be that we just didn't study enough subjects. We didn't recruit the right subjects. We had a selection bias caused by a dropout in your sample. So there are a million reasons Why that? No, it's not a million reasons, but it's a limited number of reasons. But there are reasons why you essentially could fail to reject that null hypothesis. So this 1 minus beta is referred as the power of the test. And this is now the point that I made before. Statistical significance is not identical with practical significance. If you have a large enough n, you will find significant differences of comparisons that essentially do not really deserve that much attention that they may get, just because they're significant. So it really determines, it's really important to keep in mind that it's really the actual difference, whether this is clinically relevant or not. So if you have a blood pressure medication that costs a tremendous amount of money and that only costs a marginal lowering of the blood pressure, essentially you will not get that attention, you will not get that money and that approval for that drug. So this is basically what this implies. Good. Any questions on the topic? It's quite logical, it's an important topic, right? It's like, particularly when you go into the direction of biotechnology management and you're reading protocols, you're reading studies that have been conducted with whatever biotechnological device you have used on your population, and you want to see a risk reduction, for example, you need to understand what data you're looking at. And I think this is where this is relevant for that course that you're essentially completing and that degree that you're aiming to achieve. So it really makes a lot of sense that you do understand the underlying statistics, that you do understand how to derive at these points and what components of hypothesis testing you really need to pay attention to in grants that you're reviewing, funding proposals that you're reviewing, or studies that you write yourself. So, any questions? Any questions from you guys on Zoom?
Not at the moment.
Not at the moment? Good. Sounds good. So then essentially we can briefly look at graded lab 2. So please really review these slides. So these things will really come and will be relevant for the quiz as well as for the final project. So you will definitely need to do hypothesis testing, and you will need to know how to posit research questions and how to translate them into null hypothesis. So this is really quite central. Good. So I don't know whether you can access the canvas now. Can you access canvas? Or is this really just me? Yeah? You get back on. I don't know.
I can access it.
No, it works. There was a temporary blackout, huh?
No, it was connected all the time.
No, I wasn't able to get in. That's weird. All right. I was already afraid to lock me out. All right. So if we go on assignments, or you can also go into module, it's the same thing. We go to graded lab 2. So this is for today's module. So what is being asked from you is essentially to download the subset. You're being asked to inspect and describe the data sets and the variables included and the parameters of these variables. Secondly, you're also asked to calculate the confidence intervals of all continuous variables in the overall population. Males coded as 1, females coded as 2. So this is already the first thing you need to pay attention to. It's like it's 1 and 2. So this is an enhanced subset, and the enhanced subsets always code 1 and 2. And this is, I've mentioned this in the past already. This is because they had used mainly SAS for the analysis. And you will need to, for R, I highly recommend to either recode it in a factor, which we know already how to do, or in a numerical variable, male equals 0, for females, or males equals 1 for males. This is usually a valid way to approach this. So this being said, you essentially want to compare males and females in terms of blood pressure to the normal blood pressure of 120/80. So you will basically do a set test here by computing confidence intervals of your blood pressure. So if you're looking at a null hypothesis, so you can posit here the null hypothesis for a one-sided and a two-sided test. You compare both males and females using R. You can either do this by simply looking up on Stack Overflow how to do a one sample a set test, or you can also calculate it, because it's pretty simple to calculate, right? So you just need the set test. You just need to calculate the set statistics, which is, as we know, the difference between the sample mean, which is here males and females, minus the population mean, divided by the standard error of the mean. Based on that, you will draw a conclusion. This conclusion will be based on that calculated set score and the corresponding p-value. That's easy, right? It's basically just that example that we just discussed with the serum cholesterol, but just using actual real data from the NHANES. So you just need to calculate differences divided by the standard error of the mean. And as a consequence, you get a set score. You calculate or you look up the p-value corresponding with the set score, and you're accepting or rejecting the null hypothesis for males and females, considering so it's essentially a t distribution, because I did not give you the standard deviation. So it's a t distribution. So you need to use the t distribution. So essentially, you draw conclusions based on that. What you do then in the next step is you compare the blood pressures in those older than 60, males and females separately again, from the blood pressure of 120/80. So you do the same exercise, but only in a subset of participants that are older than 60. So you have systolic and diastolic blood pressure given, and just compare both. So compare them independently. Compare the systolic from 120 and the diastolic from 80. Any questions on that? Well, we can stop together a bit, since we have half an hour. Firstly, you download the data set. This is the same as we always do. So we do BTM in class. So you basically, I have the data set down here already. So you basically open our studio. Then you just need to copy the address. So I hope nobody has any problems anymore with getting path name. I think this is quite easy at this point, right? I think it's becomes very intuitive then at one point. So you create a new script. Okay. So this is read.csv. Packing that in a DF in a data frame. Just make sure that you also start commenting on your codes. Please make sure that the commenting is good for the graded lab. I have implemented that in the rubric. So if comments are not appropriate, that there's no commenting on what you did with each line, not with each line, but with each block, I'm actually gonna draw some points for that. Okay, so we have now this data frame. So what parameters do we have in the data frame?
Professor,
Yes.
by commenting, do you mean like what question we are attending, or what is like what's exact comment do you mean? Like,
Yeah, you
because in
remember.
my grade, like in my graded lab, what I do is like every question I add the line what's the question, and then I write do that particular code, and then I do the second question. I write that question, and then I do it.
Okay, no, that's good. That's good. But just make a little note with commenting. So commenting is really where you're helping your future self. You remind yourself, okay, what did I do with this line, right? So like here, for example, I do reading the data. But yeah, it's like with the questions, I think that's a good approach, but give yourself a little bit more help. So if you want to revisit that code at one point when you code your final project, I think it makes sense to give a little bit more comment. But if there's some logic of what you have written and what you have commented on, I think that's fine. Then I'm not too picky on that. But I'm just flagging it. It's important that there's some logical flow of information, also in terms of explaining what you did with each line. The most important thing is that it's understandable what you have written and what you have coded. And the reason for that is really, I think I've mentioned this example, is like sometimes when you submit papers, when you write grants, you get comments back, and essentially you're revisiting that a year later. You will not, and I repeat, not remember what you have coded. And this is really a problem. And this, every analyst will confirm that to you. It's like what you comment will help you down the road. So this is why I'm a little bit picky on that, and then just mention it explicitly. So, but yeah, if there's some logical flow of information and you have some comments in there, I think that's good enough. And I've seen your code, so I think it should be fine. All right, so we know now what's in there. So we have systolic blood pressure in there. We have diastolic blood pressure in there. Now we can do a summary DF. We just look what's going on in here. Whether there are any missing values. So there are no missing values. So that's already good news, right? So now when we want to compare now, so we have gender included. So we want to make, okay, so I usually go first block is reading the data. Let me extend it a little bit. So I do a first block, I do reading the data. Second block essentially would then be recode the data. So if we, for example, if we have male, yes, no, it's df male, and we create a male variable is if else df gender equals 1, then it becomes a 1. If it's not, it becomes a 0. So this is how you get already male coded, and then you can, with some, you can already approach df male, and you basically get a okay, not like this. So you can calculate already. So you had 48% of males in your 1,000 participants. So now you can create subsets. So now create the subset, which is df male. So that's one way to do it. You can subset it, or you can implement it in your code, right? Both is possible, both is legit. I'm doing the subsets because otherwise these lines become too long. So df male would then be df and the brackets where df male equals 1, right? Analogously, df female would be where df male equals 0. So that's just the same kind of, oops. And of course you need to make commas after the actual criteria, otherwise you don't get what you want to get. Okay. So now, if you want to do a set statistic now, how would you do that? So you calculate the set statistic. You have a mean df male. Mean df male is mean df male, no, mean df SPP, df male SPP And this gives you a mean of 127.38. The same thing you can do with females. To DF female. As you can see, the blood pressure for females is lower. And that's a common scenario that you will see. Essentially, that's a hormonally caused dynamic. Females do have lower blood pressures than males. That's well established, well known. So now you want to compare this to a population mean. What's the population mean? So your mu is 120, right? So we have a mu SPP and we have a mu DPP, which is 80. So we make this mean SPP. We can make this mean DPP. We just have to recalculate it and relabel it. So we get mean DPP. So now we have all the variables that we need. Again, the systolic blood pressure for males is, okay, let's start off with cleaning the environment. Emptying the environment. RM list equals LS, cleans everything down. Now we have TF male. Here we get the 127, 122 for females, 73 for DPP male, 67 for females. Here we have our mu's. Now we need the standard deviation. And this essentially is easily calculated, but just you can replace the means with SDs. Since there are no missing values, you're safe to just do SD. You remember if there are missing values in there, either you remove them with which is an A, or alternatively you add NA.RM equals true. That's another way how to put this. Let's make, for the sake of completeness, let's include this. So now we're calculating the standard deviations. So this gives us the standard deviations. Standard deviations between males and females here quite comparable with 14.15, 14.67 or 68. So for the DPP and SPP, kind of comparable. A little smaller here for SPP females. Good. So now, what is next? We need the standard errors, right? We need the standard error for the females. SEM, SPP, male equals now SD, SPP, male divided by square root of length DF male DF male SPP gives us the standard error of the mean, which is here 0.84. So we have, again, so this is the length. Length gives us the length of the data set, which is 479. The standard deviation divided by the square root of the length gives us the standard error, which is here 0.84. So this is a large sample. So there's a good chance that our males at least are going to be significantly different, right? So now let's do the same for females, and we get SPP female SD SPP, yeah, female gets us 0.95. 0.95 essentially is a little larger. So let's see. So now we want to compare. And now remember the formula, right? This is now our set statistic. The set statistic is calculated as our X bar minus the mu divided by the standard error of the mean, right? And this is being accomplished by taking the mean SPP, male, minus 120 divided by SEM SPP male. So that's our set statistic. No, actually we need the T statistic, we said, right? So we need a T score. So the calculation is the same. The only thing that changes is that we are now having different alpha levels. So we have T SPP male. And now we need a T distribution. We need the T score, which we get from our table. So this is our T distribution table. So we have a really large sample size. What happens if we have a large sample size? Everything greater than 30 in terms of sample size. So the reason we need a T distribution is because we are estimating the standard deviation from our sample. And we don't have it given from the population, right? That will always prompt you to use T distribution because you're resembling the normal distribution. You're estimating the standard deviation. And that's when you use the T distribution, which follows different principles. However, since it's greater than 30, and it's actually greater than 500, you're looking at a T-score of 1.96. And this T-score of 1.96 is identical with the Z-score of 1.96 that you would need to indicate an alpha of 5%. So essentially, you can use the same values to essentially use them as thresholds. So this being said, with your T-score of 8.8, are you rejecting or are you accepting the null hypothesis? And that's $1 million question here. Because the way you're reading this T-score, you are finding your degrees of freedom, and your degrees of freedom for your sample of 479 men is essentially 1.97, or it's somewhere between 1.97 and 1.96, but let's not lose ourselves in detail. So it's 1.96. So let's assume this as being our critical threshold. If we're getting a T or a Z score exceeding this threshold, we are rejecting the null hypothesis. As a consequence of that, you have a significantly different sample mean from your population mean of 120, because the T score or Z score is greater than the critical value needed here to reject at the alpha level of 5%. Okay? Does that make sense? Are you with me?
Yes.
Good. So if you're doing the same thing now with the females, so you calculate T SPP female, and you're taking your mean SPP DF female, is this guy, minus 120, and you take SEM SPP female, what do we have now? Now we have 2.8. Are we rejecting or are we accepting the null hypothesis? The threshold is 1.96. So you're rejecting again, because it's greater than the threshold. Okay, and this is how you would approach this. If you were to do a set statistic, let's do a set statistic instead. Let's calculate this exact p-value. So we have now, let's look up the females. Let's do 2.8. 2.8 is now a probability of, let's take minus 2.8. That gives us everything to the left. Minus 2.8 is 0.026. If we were to multiply this by 2, would we reject then? Because now you're multiplying it by 2. You're assuming a two-sided test. Now you would actually not reject it. So this is where T distribution is kind of in the extremes. It's not as accurate. So the question is really, we want to calculate now the actual p-value, right? So we want p equals 0.026. This is our p for one side. Multiplying it by 2 is now 0.052. Is this larger or is this smaller than 5%? Are we rejecting or are we not rejecting? Okay, we're still rejecting. So this is P female. So this is the actual p-value for the females. For the males, it's not even possible to calculate anymore because it's not on the chart anymore, so it's so small. Yeah, so this is. So if you have a very small p-value, you would actually state it as follows. You would basically make this a character statement, and you would say it's smaller than 0.001. Ah, this is 001. So you're basically you're saying it's so small, it's not on the chart anymore. Okay. So this is that example. So this is all that is needed for the graded lab too. Well, you need to do it for the other examples, right? So you need to do it for the females, you need to do it for DPP, you need to comment it through, but then you're done with graded lab. So it's not difficult, right? It's basically employing what we just discussed. Any questions on that?
Not at the moment.
Not at the moment. Good. Well, I think that we can conclude for today.
All right.
Any questions on anything else, like on the final reports?
Not even thinking about the final reports yet.
Well, I would start sometime soon.
Okay, for sure.
Makes sense.
Yeah.
All right, sounds good. Okay, then I stop the recording and we can conclude a little earlier today. Alrighty.
Thank you so much, Professor.